watch bull math.
Hello everybody, and welcome back to another episode of F.O.A. It's your boy F.O.A, aka Nuptial of Failures here, and today we're going to be resuming talking about the stack that we made last time. If you haven't seen that episode yet, I encourage you to go check it out. It was a lot of fun. But what we essentially did was we, created a stack in Minecraft and kind of looked at how that worked. And I did mention briefly in the video that this stack was inefficient, especially compared to how they're normally implemented. So the idea for today's video is we're going to kind of talk about why this stack isn't the most efficient, what I even mean by that, and then we're going to look at how stacks are more efficiently implemented, but we won't be doing it in Minecraft because I haven't figured out quite how to do that, but that will be maybe a little challenge for you to try and figure out.
The inefficiency.
Okay, so what do I mean by this stack is inefficient? Well, when we think about efficiency, that's all about, how quick something can get done, right? And so the idea with a stack is, how quick can we store and retrieve our data? And one advantage of a stack is, ideally we can do it pretty quickly, right? Because we're just accessing what's on top. But the problem is the way we've implemented it is there's a lot of other processes. So let's recall kind of how our stack worked. So we put it into push mode and we load some data on and we push it onto the stack. All right, so then it goes down below and it gets stored. So that's the top of our stack. And we could do this several times. And every time we push new data, the old data gets moved along and that makes room for the new data, right? But the problem is that there are multiple operations happening here whenever I add a new piece of data, right? Let's say I push another piece to the stack. We would have to move these 3 pieces of data first, right, to go to the next position, and then add that new piece of data. So by the time that we have, let's say, hundreds of pieces of data, right, we just imagine we extend this design here. If we have hundreds of pieces of data in here, when I want to push a new piece of data to the stack, I'm going to have to move hundreds of pieces of data over in order for that new piece to get added to the stack. And so you can kind of see that once we start getting more and more data, this becomes less efficient because we keep having to move all of our data every single time. The same story goes with popping, right? If I put this into pop mode, once I pop this piece of data here, it goes up, but everything else has to move back to take its place. So again, if we imagine I have hundreds or thousands or millions of pieces of data in my stack, which isn't reasonable considering computers, they deal with a lot of data, right? So if I have all of that data in my stack and I just want to access one thing, accessing one thing can turn into millions of operations my computer has to perform now, right? So this becomes very inefficient. And so the fact that how quick the operation goes depends on how much data is in my stack. We say that this operation runs in big O of n time. Now you don't really have to worry too much about what that means, especially considering we haven't even talked about things like variables on this channel yet. However, that's just kind of what we call it for this sort of behavior, where doing one operation kind of depends on all of the data that's already there. Ideally, what we want is for kind of a fixed amount of operations to happen every time. Ideally, we just add the piece of data, maybe a couple other things happen, and that's it. We don't have to shuffle all of our data around. And ideally, we just remove a piece of data, right, popping from the stack, and maybe a couple other things, but nothing else happens. We don't have to move all of our data back in place like this design is doing. So how do computers get it faster?
Linked lists.
So let's imagine we've got some storage spaces in the computer's memory, right? So I'm just going to represent those as some boxes here. And each of those spots in memory kind of has an associated code with it. Just to keep it simple, I'm just going to write a number kind of to represent each spot in memory. So maybe I'll do something like 258, 43, 794. And I'm not putting these in order because the data that we're using doesn't necessarily come in order in the storage because maybe, these spots are getting used for other things in storage, or again, if we are manipulating our stack a bunch, maybe these things are getting moved and added, right? So our data isn't necessarily going to all be in kind of this super nice set up where it's just in order in terms of where it is in storage, right? So this just represents, okay, I'm in kind of storage slot 258, 43, and so on and so forth. And then in our kind of data spot here, well, we're going to put a few different things. So we're going to store the actual data. So maybe I'll just write data 1, data 2, and so on. Okay, so that's the actual content of what we kind of care about. And then the next thing that we have kind of to store is something called a pointer. So what a pointer is going to do is it's basically going to kind of point to another spot in storage. And so, for example, with data 5, if I put the pointer 2002, well, what that's telling me is that this kind of piece of data here is sort of pointing towards this piece of data right here. So now there's kind of a connection between this data in spot 11 and this data in spot 2002, where I can kind of reference this and then move into spot 2002. And I can do the same thing in my spot for 2002. Maybe I'll put a pointer for 794. So that means now that this data has a pointer going towards the data in spot 794. And we can kind of continue this chain to just kind of connect everything as we go, right? So we got 43. And maybe I don't have a pointer in this piece of data here. So this is what we call a linked list. Because, well, all of our data is kind of linked from one to the next using the pointers, right?
Linked list implementation of a stack.
We can actually use this to implement a stack. We see it kind of already has this sort of stack structure where we can maybe say that this right here is the top of our stack, and this is the bottom of our stack. And we see that it's ordered, right, by these pointers. Okay, awesome. So now let's look at how pushing and popping would happen with this stack and why it's going to be more efficient. So let's say I introduce a new piece of data that I want to push onto my stack. So I create a new piece of data and, that's going to be in some sort of memory position. And so now what I need to do is I need to take my top piece of data that's currently there and I need to add a pointer to it. So now this pointer is going to be pointing towards this new piece of data. So that's kind of what is effectively putting it into the stack, right? And we just changed the labeling where we don't call this the top anymore because it's pointing to something else. We're going to call this new piece of data the top, right? Because now it's at the top of our stack. So we see here that we don't have to do any shuffling with the data, right? Because the order is kind of kept with the pointers. And all we're doing is we're just adding a new piece of data and we're modifying something of the previous piece of data. And we don't have to do anything else, right? Because we can just kind of keep adding to the front of this by using these pointers, we don't have to change the positions of anything. This is what we call dynamic storage, right? Where we don't have a fixed amount of space that we're working with. We can kind of just keep adding to this indefinitely by extending this pointer chain, right? So let's do another one. Let's maybe add another piece of data, right? So I've got number 7. All right, so then to push this onto the stack, all I've got to do is just add a pointer into my previous data part. And now it is pointing to this new piece of data in the stack. And since this isn't pointing to anything else, this is going to be our new top of the stack that we can easily access. Right, so all we have to do is these few operations. We add the data, we assign the pointer in the previous one, and then we rename the new data to the top, and that's it, right? So these 3 operations occur every single time we add new data, whereas in the Minecraft world, we had, at this point, if I added this new piece of data, I would have had to shuffle 1, 2, 3, 4, 5, 6 pieces of data all the way back, right? So that's already way more operations than what we're doing when we add to it every time. And this efficiency, is going to compound the more we do this, right? Imagine if we have millions of pieces of data. Instead of shifting millions of data, we're just doing 3 operations, adding the data, assigning the pointer, and relabeling the new data to the top. So now let's look at how to pop from the stack. So the way we can pop from the stack is we're going to essentially want to remove this piece of data right here. So we can do a couple things. First of all, we can access what's there, right? Because we probably want to do something with that data, not just get rid of it. So we can access what's there. And then what we need to do is we need to dissolve this pointer, right, to kind of effectively remove it from the stack. So what we do is we go to the second piece of data, right? This is our data 6 here, and we essentially just get rid of the pointer, right? So we remove this pointer to 210, and what that effectively does is it dissolves this arrow right here, and so now this piece of data here is totally disconnected from the stack. Then what we need to do is we need to reassign our second piece of data to the top. So now it's the first data. So now our data 7 is completely out of the stack and it's not called the top anymore. And since we've accessed it, well, we can either do something with this, right? Move it to a different spot, maybe into another stack, or maybe we're done with this data so we can just kind of completely dissolve it from the system's memory, right? But either way, all we're doing is we're removing the previous pointer and we're relabeling what's on the top. And to summarize push, just so that I kind of have both here, what we're doing is we assign a new pointer to the new data, and then we relabel the top. Okay, so let's pop one more time. So if we want to remove the top from this stack, well, we have to get rid of the pointer in the second piece of data. So that says data 1 here, right? This is the second piece of data in the list. So we have to remove the pointer. And by removing this pointer, that's going to dissolve this arrow here. And then we also just reassign the name to the top over here. So now this is the top of our stack and our old piece of data is completely disconnected from it, right? So we've effectively popped it off of the stack. And then we can do whatever we want with it. Okay, so this is how we push and we pop using linked lists in a stack, and each time it's a small fixed amount of operations that doesn't depend on us having lots and lots of data, right? So it's a much more efficient way of actually implementing these linked lists in computers, right?
Concluding thoughts.
Alright everyone, that's going to do it for me today. I hope you found this video interesting. Once again, this journey with stacks has been a lot of fun, and I hope you've found it interesting too. Today we have learned all about kind of efficiency of stacks, and we see that, you know, my stack design, well, it's pretty epic. It is by far from efficient. And we've seen kind of a more efficient implementation of stacks by using what are called linked lists. So I hope you found this interesting. Hopefully you understand stacks even better now and kind of how we care about efficiency when it comes to things with computers and computation. And once again, I challenge you, try and come up with maybe this linked list design in Minecraft using minecart chests or other things. I'd love to hear your ideas and see what kind of designs you can all come up with, because there's people out there who are a heck of a lot smarter than I am. So with all that being said, you have a good one, you stay groovy, and I'll see you in that next Bowmaths video.
Bowmaths.